Good afternoon. I'm Sergio, and I'm talking in the extreme south of Brazil. I will present a learning object designed to improve the electrical machinery laboratory. It is a configuration with two interconnected synchronous machines that expand the potential for significant learning in electromechanical energy conversion. In the photo on this slide, we can see students in the electrical machinery laboratory at the Federal University of Rio Grande do Sul. This laboratory was built in the early 20th century. At the beginning of the 20th century, the main objective of the machine laboratory was to train engineers to operate power generation plants. In the first and second photos, we can see the university's electrical machinery laboratory, which was also a power generation plant in the city of Porto Alegre. In it, students are operating the thermal generation plant. After the 1970s, the machinery laboratory was consolidated as a teaching space for training in the operation of electrical machines. Demonstrations of the machine's behavior are also conducted in the laboratory. The measuring instruments used for the demonstrations were analog and very simple. With the improvement of measuring instruments, and the application of computers for data acquisition, the machine laboratory now determines machine performance curves and even performs the commissioning of equipment developed in research. This work is a new bench to learn the concepts of electromechanical energy conversion of synchronous machines. Using two interconnected brushless motors, it is possible to observe and act on the processes of conversion of electrical energy into mechanics and vice versa. Such a configuration is known as synchronous feedback. A new instrumentation and data acquisition system is added to the new object. The system's real-time reaction to student actions results in the development of meaningful learning. Initially, we need to clarify our understanding of the design of a learning object. When talking about objects in technology for education, soon comes object-oriented analysis and development. But, as Parrish tells us, creating activities for learning and creating instructional content are not software engineering. The development of object-oriented software creates highly hierarchical and segmented content. Contrary to what one might imagine, learning does not happen, in our understanding, when the subject tries to organize what is already organized. As Hakkinen says, to believe this is to ignore the fundamental principles of human learning. This is even more true when it comes to complex cognitive tasks. It is also necessary to clarify what is being researched. We seek to develop a constructivist learning object. We are not interested in a constructionist environment, where the student would build his own electric machine. What we want to be learned is consolidated, complex and formal knowledge. Action-mediated learning, if there is one that is not, can take place on an object that a student builds or on one that he investigates. In both it is necessary to understand that knowledge is built operating on the object and, even more importantly, on the mechanisms of the action itself. Regardless of whether the object is built or not, it needs to offer space for action and reflection on the action. Only then can an object produce meaningful learning. To make it even clearer, let's look at the following example of practical constructivism. Imagine that, in a makerspace, we want to build a solar boat. For electrical engineering students, the construction of the boat's hull would be of little interest. They would be busy making the most of the panel's energy, control the consumption of batteries, and start the engines. For such students, a boat already assembled, where it was possible to modify the control systems, would still be an object for significant learning. We will define some requirements for this learning object. For it to be useful in understanding the phenomena of energy conversion, it must, reacting to student action in real time, present these reactions in more than one way: sonic, tactile, luminous. constitute a totality that can be differentiated from the student's action and reintegrated as a result of a formal model. Have a mathematical model that can be generalized to other synchronous machines. Dispense the use of elaborate scripts. Have low cost and be safe to use. We understand that these are not simple requirements. Synchronous feedback, however, as presented, satisfies them all. But what is a constructivist design? For us, it is the one that results in an object that can follow the awareness process, as understood by Jean Piaget. Let us look at the balance on the slide, reading from the bottom up. Awareness starts with intuition dominated by perception. Beside, this perception is increased by an object that, in real time, behaves reacting immediately to the learner's action. At the intermediate level, the awareness process is dominated by concrete operative representations. The object, in turn, presents visual representations of the variables directly or indirectly observable. Finally, at the top level, awareness of formal representation will take place. The object will allow this representation because it is supported by a rigorous model. We should note that the classic electrical machine laboratory rarely exceeds the first level. Synchronous feedback is a standardized test by the IEEE to measure the temperature rise of synchronous machines under load. It is carried out with two identical machines, connected to each other, so that one of them, being the generator, provides electrical energy for the one that behaves as an motor. The motor mechanically drives the generator, forming a closed loop. A third machine will compensate for the losses, starting the rotation, keeping the system spinning. The behavior as an motor or generator will depend on the load angle between the machines. In this assembly, the loading angle can be varied by means of a rotary lathe table. The formal model, presented here, was specially developed for this work. From the phasor diagram, an equation was found for the value of the synchronous reactance of the machines. The synchronous reactance is assumed to be the same because the machines are the same. Once the synchronous reactance is known, the values for the armature voltages can be obtained. With the calculated values, the phasor diagram is presented in real time to the student. To our best knowledge, this equation is an original contribution of the work. The built workbench consists of the following parts. Letter A. The loading angle between the machines is varied by a rotary table, normally used in mechanical lathes and milling machines. Letter B. Two brushless motors with permanent magnets, which behave like three-phase synchronous machines. Letter C. A torque transducer to check mechanical power. The transducer is not mandatory. Letter D. Interconnection relays. Letter E. DC motor to compensate for losses. Letter F. Electrical interconnections. Letter G. Aluminium support structure. Letter H. Elastic couplings without gap. We can conclude by stating that the instrumented workbench, for synchronous feedback, is a new object for significant learning about electromechanical energy conversion. It allows the student to learn when operating the system, in an exploratory way. Thus, it monitors the system's behavior in real time, and performs detailed analysis from the collected data with ease. The constructed object meets the requirements to support a complete awareness process. The Federal Institute team that worked on this work is formed by Professor Tiago Reichel and graduate student Oscar Kramer. Engineer Jessica Gantz, also responsible for the work, is currently a graduate student in electrical engineering at the Federal University of Santa Catarina. Thanks for the opportunity.